We're going to talk about the seismograph. Seismograph is an instrument that is used to record and detect seismic waves. We'll talk more about seismic waves later. And it looks like this. So here is a machine and it has a ball that's hanging from a pendulum. Now that pendulum will swing back and forth. It's going to be contained within an airtight container so that no wind can influence it. And literally what it's doing is it's tracing the movement of the ground. So the amount of ground that moves, if it moves back and forth like that, it tracks there. And then here it's moving even more and it tracks that. So it's basically just something that's drawing it. I mean, you could make your own. You can just like create your own. It's just like a marker that would be hanging down from a string and it makes contact with a piece of paper. The paper gets fed through. And then as the earth shakes or whatever table you have it on shakes, this piece of paper gets produced. That piece of paper is what's called a seismogram. So that is the piece of paper that's resulted from it. And then you would track this. Now you can use that piece of information to tell you more information about the earthquake, like where did the earthquake come from, things like that. So this is what we're looking at here for a seismograph. And here's a quick little silly cartoon that most people don't find funny, but I'll put it up here anyway. Is there an earthquake happening? No. And in a pinch, a lie detector can double as a seismograph because they both produce that little paper right there. Yeah, not a great joke, but that's okay. Now, this is a seismometer, excuse me. So a seismometer is basically the most updated version of it. So do they still use the seismographs? Absolutely. Same principle, but it's all just done electronically here, and then you can just send that data out, and then that is called a seismometer. So for example, I believe one of the newest rovers that went to Mars was equipped with a seismometer so it could detect seismic activity on the planet and then send that back to us so they could be tracking Mars quakes there and finding more about the interior of the Earth, just like tracking earthquakes here allows us to do the same thing for Earth. Now, this is what's known as a seismoscope. Seismoscope was created a very, very long time ago in China. So you can see this is, 6 feet in diameter. It's a pretty big object here. And it actually works a lot like a weather vane. So a weather vane is a very simplistic weather instrument that only tells you the direction that the wind is coming from. That's it. Nothing more than that. It just says the wind is blowing this way, right? So this works in actually a very similar way. See how there's another pendulum right in here? And if the pendulum swings too far in a certain direction, then it opens up and there has all these dragons that are surrounding here, and the dragon is holding a ball inside of its mouth. And then it releases that ball and it falls into the frog's mouth. So basically, if there's no earthquake, nothing happens here. But if it does work, if there's an earthquake that happens, even if you can't feel it, this machine is more sensitive and it detects it, and then it releases it, and it'll say, okay, the earthquake came in that direction. Now, when this machine was first unveiled, not a lot of people were really convinced that it worked. So there was this famous story of a certain leader at the time who wasn't quite convinced that it worked, but all of a sudden, there was a ball that got released and nobody felt anything. So they're like, is this just faulty? Is this broken? And then a couple of days later, a rider from that direction, several miles away, came and said, hey, there was this huge earthquake that happened over here. We need supplies. Please help us as best as you can. So ever since then, it was known to be much more legitimate of a detecting device. So now this is another term we're definitely going to need to understand. It's called the Richter scale. Now, when we talk about a scale, a lot of us think like the scale that you step on and it weighs you, right? That is a certain form of a scale. But really, it's measuring you in the scale that it's really talking about is it's talking about, well, you could weigh as little as 0 pounds or as many as a lot more than that, right? And like where on that range of pounds do you exist in? And it's similar to this. The Richter scale is measuring the magnitude or the strength of earthquakes. The scale goes from normally about 1 to 10. In theory, you can go below that, like as low as 0, but there's basically nobody could measure that. And in theory, you could go above it, but again, not really ever something that's been measured on those two extremes before. So generally, the scale goes from 1 to 10. So after you get your seismograph, you're reading over here, and you produces something, you're going to say, okay, based on what we said, this is a 7.0 on the Richter scale. That's how you're going to measure the earthquake. So let's talk about some of the details about it. We start from anything less than 2.0 is considered to be a micro earthquake. So It can only be felt by seismographs, so people are not able to even sense them. There's millions of these per year. You're going to notice that as the magnitude of the strength increases, the frequency, or how often that they happen, goes down. 2.0 to 2.9 is a minor one. No building damage here. Over a million per year, so a lot still. 3.0 to 3.9 is when people, if you're like very sensitive to things shaking, if you're just naturally able to pick up on that, you're going to start to notice it, and you might be able to see like certain objects that are kind of pendulum based might start to swing back and forth a little bit. I would assume that this is pretty similar to like if you live near a train tracks and like the train goes by, like that's like a mini earthquake that you'd be like experiencing there, but you understand why it's happening. So that's 100,000 per year. If we get to a light earthquake, 4.0 to 4.9, most people now feel it. Indoor objects shake or fall to the floor. Fun fact, if you are a 4.5 earthquake or above, any seismograph station, so any legitimate station that has a seismograph anywhere in the world, is able to pick up on it anywhere. So even if it's on the opposite side of the world, they can still detect it. So that's at a 4.5. That's how strong those machines are. 5.0 to 5.9, there's only about 1,000 of them per year. Notice how we were up to over millions, now we're down to 1,000. These are able to damage or destroy buildings that are completely not ready to withstand those earthquakes. So in a place that maybe doesn't have a lot of money to build up their buildings to reinforce them, or just a place that is not used to experiencing earthquakes, they're going to be the most at risk to it, and everyone will be able to feel those. 6.0 to 6.9 is considered to be a strong earthquake, so it's going to shake very far away from where the earthquake originated from. It definitely does damage to buildings, about 100 per year. 7.0 to 7.9 is a major earthquake, widespread damage in most places, 10 to 20 per year. 8.0 to 8.9 is great. Not great in the terms of like, oh, this is such a great thing to be happening. It's just like considered to be like a rare and powerful event. Same thing with 9.0 and 9.9. It does damage to most buildings, even the ones that are very built to withstand it. And then you see how the frequency starts to dip down from there. 8.0 is only about 1 per year, and then a 9.0 only happens every 5 to 50 years or so, in that range. And there's never been a 10.0 or over recorded. So just to give you some context, the dinosaur extinction event, when that asteroid hit the Earth, I mean, that killed off 75% of life on Earth. That one would have registered, like, let's say an 11.0 on the Richter scale. Of course, there was no Richter scale. There was no earthquake detecting machine at the time, so there's no way to know exactly what it was, but that's what they estimate, the amount of energy that was released. When Theia, the protoplanet, crashes into Earth and it changes us back into this magma-like planet, right? And then it just wiped off any land or anything that was ever alive at that point, all gone. That was, let's say, a 13.0 on the Richter scale, right? So it's in theory possible for it to happen, but it's like this outside, it's not something that the Earth would just do on its own, right? It wouldn't have like on its own, we're reading that there's a 12.0 on the Richter scale today. That's not, I don't think that the Earth would be able to generate that by itself without an impact event. So here's all that same information. If you want to pause and read it, it's pretty interesting. Just gives a little bit more detail on the impact. And then on the far right, it shows like the building damage that would happen visually there. So you can see how it would just be more structurally damaged there until it just completely collapses. And there are certain areas, like there's certain areas that are prone to get these earthquakes, like we talked about already on the west coast of the United States. So you would imagine that they have invested more money into building up new structures to withstand earthquakes so they don't collapse, as compared to on the East Coast, like in New York City. I'm assuming that there's probably plenty of older buildings that they never reinforced to withstand earthquakes because it's just such a rare and unnatural event there for them to experience that. And here's another just visual representation of the Richter scale, the types of things that you might expect to happen there. So you can pause and read through that if you're interested. This is a great video that just shows visually, like if this is a 7.8 earthquake, that's how much stronger it is than a 7.0 that's right there, and this is a 6.9. So the way that it increases is if you go back to it, right? It's not that a 2.0 is twice as strong as a 1.0. It's like 32 times stronger than that. And then a 3.0 is not 3 times stronger than a 1.0. It's like 1,000 times stronger than that. A 4.0 would be 32,000 times stronger than that. A 5.0 compared to 1.0 is over 1,000,000 times stronger than that. So it like increases very, very fast in terms of the raw energy that would be produced. And this is a great visual demonstration of that. This right here is a very famous event that I have a couple videos for you to take a look at, and it has to do with the 1989 World Series. So perhaps you know somebody that was alive during this point. I personally was not. I was not born until the next year. Oh, sorry, I was born. I was 1988. I was not conscious, right? I don't remember this, of course, but apparently, right before the World Series, there was a very interesting event, and that was that a 6.9 earthquake hit during a World Series event. So you may have heard that there's a Subway Series that happens in New York when the Mets versus the Yankees, because they're both New York City teams. In this area, it was the Oakland Astros and I believe it was the San Francisco Giants, if I'm not mistaken. So that was their Subway Series, and it happened around 5-ish during the day, 5 o'clock p.m. Normally, that would be rush hour time when there was tons of people on the roads, but instead, everybody was inside watching the baseball game. So because of that, there wasn't nearly as many casualties as there would have been normally, but it still was a very impactful event, and this video will show you some live footage of what happened during it, which is really crazy.